Hi everyone. In the first part of this video, we'll go through a demonstration of sampling distributions and the central limit theorem. That's where we stopped at the end of the last lecture, so we'll pick up right where we left off last time. I'll start by explaining everything that you see on the screen. In this demonstration, we're going to be focusing on the exam scores of 48 students who are in a certain class. We can see their 48 exam scores down here, and we can also see their 48 exam scores in this graph up here. This graph is a dot histogram. In a dot histogram, each person's value is shown as a separate dot. So over here we have all of the exam scores in the 60s. Here we have all of the exam scores in the 70s. Here we have all of the exam scores in the 80s, and here we have all of the exam scores in the 90s. We can see that the exam scores are positively skewed, or skewed to the right, because most of the students' exam scores are down closer to the low end, and fewer of the students' exam scores are up closer to the high end. The mean exam score of the class is 72. If we added their 48 exam scores and divided the total by 48, the answer would come out to 72. It makes sense that the mean of the class is 72 because that's pretty close to the center of the exam scores. It isn't exactly at the center because the exam scores are positively skewed. When a set of data values is positively skewed, the mean is above the median. In other words, the mean is pulled toward the right end. If these exam scores had followed a normal distribution, then the mean and median would both be exactly at the center. Notice how I use the word population up here. In this demonstration, the 48 students in the class will be our population. We're going to imagine that I'm a researcher who's interested in what the mean exam score of this population equals. I would like to be able to survey all 48 students in the population, record their exam scores, and then calculate the mean exam score of the population. However, for some reason I don't have enough time to survey all 48 students in the population. Since I don't have enough time to survey all 48 students, I decide to randomly select a sample of students from the population, record the exam scores of the students in my sample, and then calculate the mean of my sample to estimate the mean exam score of the entire population. Even though we can see on the screen that the population mean is 72, I as a researcher don't know what the population mean equals. That's why I'm going to use the mean of my sample to estimate the mean of the population. I'm going to hope that the mean of my sample comes out close to the mean of the population. In other words, I'm going to hope that my sample mean gives me an accurate idea of what the population mean equals. However, I'm going to have to realize that there's no guarantee that my sample mean will come out close to the population mean. Since I'm going to use a random sample, it's likely that my sample mean will fall within a certain range of the population mean. However, it's possible that my sample mean will fall far below or far above the population mean. It really just depends on which sample I end up selecting. The difference between the sample mean and the population mean always depends on which sample ends up being selected. Each sample has its own sample mean, and some samples are more accurate than others. That's why I have to hope that my sample mean comes out close to the population mean. There's really no guarantee that my sample mean will be close to the population mean. In this demonstration, we're going to look at different possible samples that I could select from this population. We'll see that each sample has its own sample mean, and that those sample means have a distribution of their own called a sampling distribution. Before we go through this demonstration, I'm going to need to choose a sample size. Let's say I decide to use a sample size of 4. I decide that I'm going to randomly select 4 students from this population, record their 4 exam scores, and then calculate the mean of those 4 exam scores to estimate the mean exam score of the entire population. If I randomly select 4 students from this population, this is one possible sample that I might end up selecting. It's definitely possible that these 4 students will end up being my sample. If these 4 students end up being my sample, and I record their 4 exam scores, then these 4 exam scores up here will end up being my data set, and my sample mean will end up being 69. If you add these 4 exam scores and divide the total by 4, the answer comes out to 69. The mean of the sample, which is 69, is just one value inside of this sampling distribution over here. This sampling distribution includes the means of all possible samples of 4 students that could be selected from this population. The students in the 4 red boxes are just one possible sample of 4 students that could be selected from this population. That's why their sample mean of 69 is just one value inside of the sampling distribution. Since these 4 students have a sample mean of 69, their sample mean is right above 69 under this curve. Let's look at another possible sample of 4 students that could be selected from this population. If I randomly select 4 students from this population, I might end up selecting these 4 students as my sample. If I select these 4 students as my sample, and I record their 4 exam scores, then my sample mean will end up being 69. If you add these 4 exam scores and divide the total by 4, the answer comes out to 69. So far we've looked at 2 different possible samples of 4 students that both have a sample mean of 69. Since these 2 samples both have a sample mean of 69, their 2 sample means are both above 69 inside of the sampling distribution. I purposely made a red dot and a brown dot so that you could see that the red dot is the mean of the 4 students in the red squares, and the brown dot is the mean of the 4 students in the brown squares. There are actually several other possible samples of 4 students that would give me a sample mean of 69. Those sample means are all stacked above 69 inside of the sampling distribution. Those sample means make up a column of sample means that goes all the way from the tick mark of 69 up to the curve. Let's look at one other possible sample of 4 students that has a sample mean of 69. The 4 students in the orange squares have a sample mean of 69. If you added their 4 exam scores and divided the total by 4, the answer would come out to 69. That means that their sample mean is a third value inside of this column of sample means that are all stacked above 69. Let's now look at a possible sample of 4 students that has a different sample mean. The 4 students in the green squares have a sample mean of 73.5. If you added their 4 exam scores and divided the total by 4, the answer would be 73.5. That means that their sample mean is above 73.5 inside of the sampling distribution. Just like how we found more than one possible sample of 4 students with a sample mean of 69, we could probably find more than one possible sample of 4 students with a sample mean of 73.5. In fact, if we looked hard enough, we could probably find several other possible samples of 4 students with a sample mean of 73.5. Let's try to find just one other possible sample of 4 students with a sample mean of 73.5. It turns out that the 4 students in the purple squares have a sample mean of 73.5. If you added their 4 exam scores and divided the total by 4, the answer would be 73.5. That means that their sample mean is also above 73.5 inside of the sampling distribution. These 2 dots, which are the mean of the 4 students in the green squares and the mean of the 4 students in the purple squares, are just 2 values inside of a column of sample means that includes all of the possible samples of 4 students with a sample mean of 73.5. Those sample means make up a column of sample means that goes all the way from the tick mark of 73.5 up to the curve. At this point, I would like to stop and take a look at the 5 sample means that I've plotted under the curve so far. I want you to realize that each dot is just the mean of a different sample of 4 students that could be selected from this population. If I randomly select 4 students from this population, and the 4 students in the red squares end up being my sample, then the red dot is my sample mean. If the 4 students in the brown squares end up being my sample, then the brown dot is my sample mean. If the 4 students in the orange squares end up being my sample, then the orange dot is my sample mean. If the 4 students in the green squares end up being my sample, then the green dot is my sample mean. And if the 4 students in the purple squares end up being my sample, then the purple dot is my sample mean. If I randomly select 4 students from this population, the sample that I end up getting depends on chance, which means that any dot under this curve can end up being my sample mean. I also want you to realize that the white space under this curve includes the means of all of the other possible samples of 4 students that we haven't looked at yet. If I randomly select a sample of 4 students from this population, the sample that I get depends on chance, which means that any dot under this curve could end up being my sample mean. If I get 4 students with a mean of 80, then my sample mean is one of the dots right here. If I get 4 students with a sample mean of 70, then my sample mean is one of the dots right here. And if I get 4 students with a sample mean of 95, then my sample mean is one of the dots right here. Most importantly, I want you to realize that a sampling distribution isn't a collection of individual values. The population is a collection of individual values, and the sample that's actually selected is a collection of individual values. But the sampling distribution is a collection of sample means. It includes the means of all possible samples that could be selected from the population, using the researcher's sample size. Sometimes people get confused when they hear the term sampling distribution, because the term sampling distribution sounds like it should be referring to the distribution of values inside of the selected sample. But that's actually not what the sampling distribution is. The sampling distribution is the collection of the means of all possible samples that could be selected by the researcher. By looking at the sampling distribution, you can see how the sample mean varies from one sample to the next. You can see how some samples have a sample mean that's close to the population mean, and some samples have a sample mean that's further away from the population mean. The samples with a sample mean that's close to the population mean are more representative of the population, and the samples with a sample mean that's further away from the population mean are less representative of the population. Out of the 5 samples that we've looked at already, the purple sample and the green sample are the most representative because their sample mean of 73.5 is pretty close to the population mean of 72. These other 3 samples are less representative of the population because their sample mean of 69 is further away from the population mean of 72. As a researcher, I have to hope that I get one of the more representative samples with a sample mean that's close to the population mean, and I have to hope that I don't get one of the more extreme samples with a sample mean that's further away from the population mean. You might be wondering why this sampling distribution has a skewed shape. The shape of a sampling distribution depends on both the shape of the population and the sample size. If you take a small sample from a skewed population, like this population right here, then the sampling distribution will be skewed in the same way as the population. For example, if you take a small sample, like a sample of 4 people from a positively skewed population, then the sampling distribution will be positively skewed, just like the population. Let's think about why that's true. First, we have to realize that when a population is positively skewed, there's a lot of people in the population that have fairly low values. If you take a small sample from a positively skewed population, those low values are going to have a large effect on each of the sample means in the sampling distribution, and it's going to pull those sample means downward toward the left end of the curve. That's why a lot of the samples that you could select from the population will have low sample means down here. Let's think about what would happen if I selected a larger sample from this population, such as a sample of 30 people. If I selected a sample of 30 people from this population, then the possible samples would be all of the possible combinations of 30 people that I could select from this population. Each possible combination of 30 people would have its own sample mean, and those sample means would make up the sampling distribution. Each value in the sampling distribution would be the mean of one possible group of 30 people that I might select from the population. Since each value in the sampling distribution would be a mean of 30 people, instead of a mean of only 4 people, the sample means inside of the sampling distribution wouldn't be as affected by the low values in the population. That means that the sampling distribution would actually follow a roughly normal curve, with most of the possible samples in the middle, and fewer samples out here, and fewer samples out here. What I've just explained is actually called the central limit theorem. The central limit theorem says that if you take a large sample, generally a sample of at least 30, from a skewed population, the sampling distribution of possible samples will be roughly normal, even though the population is skewed. Before we move ahead, Let's look at one more possible sample of 4 students that could be selected from this population. If I randomly select 4 students from this population, I might end up selecting the 4 highest students in the class. This is one possible sample that could be selected. If I ended up selecting these 4 students as my sample, and I recorded their 4 exam scores, then my sample mean would end up being 91.25. If you add these 4 exam scores and divide the total by 4, the answer comes out to 91.25. The mean of this sample is actually the highest sample mean in the sampling distribution. I made a dot way out here at the tip of the curve to show that the mean of these 4 people is the highest sample mean in the sampling distribution. There aren't any possible samples of 4 people that would give me a higher sample mean than this sample mean right here. So now I'm actually finished looking at possible samples of 4 people. Let's move on to take a look at some possible samples of 30 people that could be selected from this population. If I randomly select a sample of 30 students from this population, then my sampling distribution will include the means of all possible samples of 30 students that I could select from the population. According to the central limit theorem, this sampling distribution will be roughly normal, even though the population I'm sampling from is skewed. Also, since I'm using a larger sample size, the sample means in the sampling distribution will be more accurate and less spread out than they were when I used a smaller sample size. In other words, the sample means will be more closely clustered around the population mean of 72. So, if you take a large sample from a skewed population, what actually happens is the sample means in the sampling distribution become more accurate and more normally distributed at the same time. If you take a small sample from a skewed population, the sample means in the sampling distribution are more spread out and skewed. And if you take a large sample from a skewed population, the sample means in the sampling distribution are closer together and roughly normal. Notice how I changed the tick marks on the number line down here. The reason why I changed the tick marks is because of the fact that the sample means in the sampling distribution will be closer to the population mean of 72 than they were in my last example. Let's now look at some possible samples of 30 students that could be selected from this population. If I randomly select 30 students from the population, I might end up selecting these 30 people. These 30 people are one possible group of 30 that I could select. If I end up selecting these 30 people as my sample, and I record their 30 exam scores, then these 30 values will be my data set, and my sample mean will be 72.17. This sample mean of 72.17 will be one dot inside of the sampling distribution of all possible samples of 30 people. Notice how I put the dot right above 72.17. One thing that should stand out on the screen right now is that if you randomly select a large sample from a skewed population, the values in the sample tend to be skewed just like the population they came from. In other words, if you randomly select a large sample from a skewed population, the values in the sample tend to represent the shape of the population pretty well. However, if you randomly select a large sample from a skewed population, the sampling distribution of all possible samples is roughly normal, even though the population is skewed. So this is one thing that students sometimes find to be confusing. It's the fact that if you randomly select a large sample of at least 30 from a skewed population, the values in the sample tend to be skewed just like the population, but the sampling distribution of all possible samples is roughly normal. Let's take a look at another possible sample of 30 students that could be selected from this population. If I randomly selected 30 students from this population, I might end up selecting these 30 people to be my sample. If I selected these 30 people to be my sample, and I recorded their 30 exam scores, then these 30 exam scores would be my data set, and my sample mean would end up being 69.6. If you add the 30 exam scores in the blue boxes and divide the total by 30, the answer comes out to 69.6. The mean of the blue sample would be 1 dot inside of the sampling distribution. That dot would be above 69.6. So far we've looked at one possible sample of 30 students that has a mean of 72.17, and we've looked at one possible sample of 30 students that has a mean of 69.6. There's probably more than one possible sample of 30 students that would give me a mean of 72.17. All of those samples would have sample means that are stacked above 72.17 in a column right here that goes all the way up to the curve. There's probably also more than one possible sample of 30 students that would give me a sample mean of 69.6. Those samples would have sample means that are stacked above 69.6. Those sample means would be a column of sample means that goes from 69.6 all the way up to the curve. Let's take a look at another possible sample of 30 students that could be selected from this population. If I randomly selected 30 students from this population, I might end up selecting these 30 students to be my sample. If I selected the 30 students in the green squares to be my sample, and I recorded their 30 exam scores, then these 30 numbers would be my data set, and my sample mean would end up being 72.17. Notice how the green sample and the red sample have the same sample mean. They both have a sample mean of 72.17. That means that the mean of the red sample and the mean of the green sample are both above 72.17 in the sampling distribution. They're just two values inside of a column of sample means that all equal 72.17. I wanted to talk about why it's important that the sampling distribution is roughly normal when you randomly select a sample of 30 from a skewed population. When you randomly select a sample of 30 or larger from a skewed population, and the sampling distribution is roughly normal, it's possible to use the shape of the normal curve to find the probability of your sample mean coming out to a number in a certain part of the number line. For example, if I was randomly selecting a sample of 30 people from a skewed population, and I wanted to know the probability of my sample mean coming out to 74 or higher, I would be able to use the shape of the normal curve to find the probability that I'm looking for. I would be able to use the shape of the normal curve because, in that situation, the sampling distribution is roughly normal. In any situation in which the sampling distribution is roughly normal, it's possible to use the shape of the normal curve to find the probability of the sample mean coming out to a number at a certain part of the number line. There's actually three situations in which the sampling distribution is at least roughly normal, and it's possible to use the shape of the normal curve to find the probability of the sample mean. Those three situations are taking a large sample from a skewed population, taking a large sample from a normal population, or taking a small sample from a normal population. In each of those three situations, the normal curve can be used to find the probability of a sample mean. Remember that if the population is normal, the sampling distribution is always normal, no matter what sample size you're using. And if the population is skewed, then the sampling distribution is roughly normal, with a sample size of at least 30. There's actually only one situation in which the shape of the normal curve can't be used to find the probability of the sample mean landing at a certain part of the number line. That situation is when you're taking a small sample from a skewed population. In that situation, the sampling distribution is skewed, so you can't use the shape of the normal curve to find the probability of getting a sample mean in a certain area. When you take a small sample from a skewed population, there's really no clear way of finding the probability of getting a certain sample mean. In the next video, we'll go through some problems in which we use the shape of the normal curve to find the probability of the sample mean landing at a certain part of the number line. In each of those problems, we'll have to make sure that we're sampling from a normal population, or that we're taking a sample of at least 30. That's because if it turns out that we're taking a small sample from a skewed population, it's actually not possible to use the shape of the normal curve to find the probability that we're looking for. If you're feeling a little bit confused about how the shape of the normal curve could be used to find the probability of the sample mean coming out to a certain part of the number line, think about it this way. When the sampling distribution is normal, then the population mean is at the center of the sampling distribution, and there's a lot of samples with sample means near the population mean. As you go further away from the population mean in either direction, there are fewer and fewer samples with sample means out there. For example, as the curve drops out this way, there's fewer and fewer samples with sample means out here, and as the curve drops this way, there's fewer and fewer samples with sample means out here. So basically, when the sampling distribution is normal, sample means further away from the population mean in either direction are less and less likely to be reached. If I randomly selected a sample of 30 people from this population, I would be likely to get a sample mean somewhere around 72, because there's a lot of possible samples with a sample mean around 72. However, I would be really unlikely to get a sample with a sample mean down at 68, because there aren't very many possible samples of 30 in this sampling distribution that would give me a sample mean that low. Also, if I randomly selected 30 people from this population, I would be really unlikely to get a sample mean all the way up here at 75, because there's very few possible samples of 30 that would give me a sample mean that high. Before the end of this video, I wanted to talk a little bit about the mean and standard deviation of a sampling distribution. In an earlier video, I mentioned how a sampling distribution is just a collection of numbers that happen to be sample means, and those numbers in the sampling distribution have a mean and standard deviation of their own. The mean of the sampling distribution always equals the mean of the population, regardless of what sample size you're using, and regardless of what shape the sampling distribution has. So, in my first example, when we were looking at all possible samples of 4, and the sampling distribution was skewed, the mean of that sampling distribution was the population mean of 72. Since the sampling distribution was skewed, the mean of 72 was a little bit off-center, but the mean of the sampling distribution was still 72. The mean of the numbers in this sampling distribution is also 72, because like I said, the mean of the sampling distribution always equals the population mean. The numbers inside of a sampling distribution also have a standard deviation of their own, called the standard error. When the standard error is small, then the sample means are tightly clustered around the population mean, and the sample means tend to be accurate. When the standard error is large, then the sample means are spread out further away from the population mean, and the sampling distribution includes sample means that are less accurate. You could probably guess that the sampling distribution we looked at earlier, with a sample size of 4, had a larger standard error, because those sample means were more spread out across the number line. And you could probably guess that the sample means in this sampling distribution have a smaller standard error, because in this sampling distribution, the sample means are more closely packed around the population mean of 72. There's less spread to the sample means. In an earlier video, I said that when the sample size goes up, the means of the possible samples move in closer to the population mean, and the standard error goes down because the means of the possible samples are less spread out. That's what we're seeing in this video. When the sample size was 4, the means of the possible samples were more spread out, and the standard error was larger. But when the sample size went up to 30, the means of the possible samples moved in closer to the population mean, and the standard error went down. I actually went ahead and calculated the standard errors of the two sampling distributions. The standard error of the sampling distribution for the sample size of 4 came out to about 7, and the standard error for the sampling distribution for the sample size of 30 came out to about 0.88. So the standard error of this sampling distribution is quite a bit smaller than the standard error of the sampling distribution we looked at earlier. There's actually two things that affect the standard error of a sampling distribution. One thing that affects the standard error is the sample size. When you're using a larger sample size, the means of the possible samples are closer to the population mean, and the standard error is smaller. That makes sense because we know that larger samples tend to be more accurate. One other thing that affects the standard error besides the sample size is the amount of dispersion in the population. If there's a high amount of dispersion or spread between the individual people in the population, then the means of the possible samples will be more spread out, and the standard error will be larger. When the people in the population have less dispersion, and they're more similar to each other, then the means of the possible samples will be closer together, and the standard error will be smaller. So overall, the standard error goes down either when the sample size goes up or when the population has less dispersion. And as a researcher, I want the standard error to be as small as possible, because when the standard error is small, the means of the possible samples are closely packed around the population mean, and I'm likely to get a sample with a sample mean that's highly accurate. In other words, I'm likely to get a sample with a sample mean that's highly close to the population mean. There are two things that lead to a smaller standard error and help me to get a more accurate sample mean. If I use a larger sample size, the standard error will be smaller, and I'll be more likely to get an accurate sample mean. If the population that I'm sampling from has low dispersion, then the standard error will be small, and I'll be likely to get an accurate sample mean. I have control over the sample size that I'm using, but obviously I don't have control over the amount of dispersion between the people and the population that I'm studying. If I know that the population that I'm studying has high dispersion, and I know that that's going to raise my standard error and keep me from getting an accurate sample mean, I can make up for it by using an even larger sample size. If I use an even larger sample size, the standard error will go back down, and I'll be likely to get a fairly accurate sample mean. We're almost at the end of this video. Before the end of this video, I wanted to describe how I was able to find the standard errors of the two sampling distributions. I was able to find them by just using the standard error formula. There are three values that go into the standard error formula. One value that goes into the formula is the population standard deviation, which measures the amount of dispersion between the individuals in the population. Another value that goes into the formula is the population size, and another value that goes into the formula is the sample size. Before I could use the formula, I had to calculate the standard deviation of the population. I was able to find the population standard deviation using Excel. I entered the 48 population values into Excel, and Excel gave me the population standard deviation. After I found the population standard deviation, I was able to use the standard error formula. I had to use the formula 2 times. The first time I used the formula, I entered the population standard deviation, the population size of 48, and the sample size of 4. That gave me the standard error of the sampling distribution that we looked at earlier, which was for all samples of 4 people. The second time I used the formula, I entered the population standard deviation, the population size of 48, and the sample size of 30. That gave me the standard error of this sampling distribution for all possible samples of 30.